Okay, so of course, chapter 2 has been about polynomials so far. Okay, um, we have a couple theorems that we get to talk about today. One of them is this, and it seems very obvious. Okay, but we have to talk about it. So, any polynomial of degree n will have at least one zero in the complex number system. Sometimes our zeros will all be real. Sometimes our zeros will all be complex. Sometimes our zeros will be a mixture of real and complex. But for sure, we're going to have a zero, no matter what the degree of your polynomial is. Graphically, what does it mean if we have a real zero? We touch the x-axis, okay? What does it mean graphically if we have an imaginary or complex zero?
It doesn't touch the x-axis.
It doesn't touch the x-axis. Something funky happens, but it doesn't cross the x-axis. If you remember back to your parabolas last year, if you got two zeros that had imaginary numbers, that meant your parabola either started above the x-axis and opened up, or it started below the x-axis and opened down. Okay? But you still found values that made your equation zero. What this is saying is no matter what, we're going to have values that make our equation zero. Whether they're real or imaginary, we're going to have at least one. Could they all be the same number? We could have 4 of the same zeros, but we still have a zero. Okay? Let's talk about this. If a polynomial is nth degree, the polynomial is nth degree, Molly, how many zeros will we have? If our degree is n, how many zeros do we get?
N.
We get n. And if we have n zeros, and Marissa, how many factors will we have? If we have n zeros, how many factors will we have?
N.
Yes. If you have a 4th degree polynomial, then we can break it down to 4 linear factors, which will give us 4 zeros. Some of them may repeat, that's fine. Okay. What do I mean by a linear factor? What does a linear factor look like? X plus 1. X plus 5. X minus 3. X minus 2i. Whatever it is, a linear factor is x to the first power. Okay? So, by the end of today, you're going to be able to take a polynomial, factor it to as many factors as the degree, and find that many zeros. Okay? That's what we get to do between today and Monday. All right? So let's first start here. I have a polynomial with zeros of 1, -2, 3i, and -3i. I want us to write the linear factors. Okay? So Henry, if 1's a 0, what's a linear factor?
X minus 1.
Great. If -2 is a 0, Finn, what's our factor?
X plus 2.
If 3i is a 0, Kelsey, what's our factor? And if -3i is our 0, Sydney, what's our factor? That's going to set us up for where we need to go next. The rational zeros test. Some of you remember what it is. Some of you shaking your head. Dave, don't like it? Does anybody remember it? Some people have been talking about it. To have a 30-second conversation, do you remember what the rational zeros test is? Okay, we're back up here. Who remembers what it is? Gabe. You create a list of numbers. Okay. And what do you do with all those numbers? Okay, so you test them in synthetic division until you get some that work. Okay, this is how you come up with your pool of numbers. Okay, so we have a polynomial with integer coefficients. Every zero is in the form P over Q, where P and Q look like this. Ignore those. Okay, so I'll let you have a chance to write down what you want to. P are all the factors of the constant term. So whatever number is at the very end, write the constant term. Q is a factor of the leading coefficient. Okay. All zeros have the form P divided by Q. So we're going to use that to create a list of numbers. Now, this list of numbers is only going to give us possible rational zeros. It is possible that a polynomial has some irrational zeros, like radical 3 and negative radical 3. It's possible that our polynomial has some complex zeros, 1 plus I and 1 minus I. Okay? In those cases, the rational zeros test will not help us get those, but if we can find the rational zeros first, maybe we can use our factoring skills to get any that are either irrational or complex. Okay? So, here we go. Okay. We are going to make a list of possible zeros. Okay? Instead of just randomly trying numbers into our synthetic division, if we can create a small pool of numbers to choose from, it's not going to be quite as daunting of a task. Okay? So our possible zeros, we need to take factors of the constant divided by factors of the leading coefficient. So first of all, factors of 3. 1 and 3. But keep in mind, we could have a 1 and a 3, or we could have a -1 times a -3. So we need to account for both positive and -1, positive and -3. Okay? Divided by factors of the leading coefficient. 1 and 2. So what I've done is I've created a list for our numerator and a list for our denominator. But really, we have possible zeros of 1 over 1, 1 over 2, 3 over 1, and 3 over 2. Now, we're going to set up our synthetic division. 2, 3, -8, 3. Our goal is to pick one of these numbers and get a remainder of 0. Okay, Will, what number would you like to try first?
1.
1. I think it is a great idea to start with 1 and -1. Drop down the 2. Add to get 5. Add to get -3. Well, look at that, Will. You were right. What did you say? Be nice. Okay, so this means that 1 is a 0. Okay? It also means that x minus 1 is a factor. And left over, we have 2x squared plus 5x minus 3. Okay? So now we are left with a trinomial. Let's see if we can factor it. X times 2x will get us 2x squared. We know -3 has to be 1 times 3, 1 positive, 1 negative. Where should we put the 3? Where should we put the 1? Okay, 3 should be multiplied to the 2x, the 1 here. We want 3 times 2x to be positive to get a positive 6x, and x times -1 and -x. These would be your linear factors. Okay, your zeros would then be 1, -3, and 1/2. Yes.
You got faster if you, in the very first one, didn't you factor by grouping
Yeah.
with x plus 3?
You cannot factor by grouping. If we tried that, we could factor out an x squared. Left over would be 2x plus 3. We can only factor out a -1 here, and left over is 8x minus 3. Since those aren't the same, it doesn't work. Okay? These two have to be the same if we're factoring by grouping.
But couldn't you do like this, like x plus 3, everything else around that? Or does that not work?
Yeah, no, because we have to have 2 similar groups to factor by grouping. Okay. That is a good point, though. If you do see something that factors, you don't have to use the rational zeros test. It's not bad if you do, but it is probably quicker if we can factor to factor. Okay? Now, what happens if you get to here and that you can't get it to factor? What? You would have to use the quadratic formula. Okay? Let's remind ourselves what the quadratic formula is, just in case you have to use it at any point. Now, I want the quadratic formula to be a last resort. You need to try and factor. Okay? You're not going to use the quadratic formula on x squared minus x plus 6. Okay? But, if you can't get it to factor, you always have the quadratic formula of x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Never forget it. Never forget it. It's 2a. Okay? Okay? Questions on this example? Okay. The next thing we need to talk about, which kind of ties into this quadratic formula that we just talked about, if you have a complex zero, you will never only have just one of them. Okay? A complex zero with real and imaginary parts, an imaginary zero, essentially, they will always come in conjugate pairs. If you have a plus bi, you're going to have a minus bi as a zero as well. If we think about solving the quadratic formula, when we get a negative underneath, right, that's when we get an imaginary number. We have negative b plus this, negative b minus the square root. Our complex zeros will always come in pairs. This is what I want you to think about and have a 60-second conversation with your group. Is a cubic function guaranteed to cross the x-axis? Is a quartic, an x to the fourth function, always guaranteed to cross the x-axis? Talk about it.
I had sports. Can I finish that after lunch?
Okay. Yes, that's fine. Oh,
Okay.
all right, pod 6. Talk to me about the cubic function.
We say like cubic function will always have a zero.
Why?
Because no matter what, it's always going to go from that. Like, it's always this side.
You're trying to describe something to me.
Yeah, like the range.
You're kind of going like this.
Yeah.
Like what's happening with an odd degree function, left side versus right side?
There was opposite function.
They're always opposite behavior, so we're guaranteed to cross the x-axis. Anybody have a different explanation?
Complex zeros are the only times when there's a zero that doesn't touch the x-axis. And since they always come in pairs, when there's an odd one, there has to be one left over that crosses the x-axis.
Okay, complex conjugates come in pairs. Okay, so if there's an odd number of zeros, one of them has to be real, meaning we're crossing the x-axis. Good. What about a quartic function? Card 1.
Quartic function can not have a real zero because it's an even function. It has to have an even number of zeros. And they could
all be. Okay, they could all be complex. 2 could be complex, 2 could be real, or all 4 of them could be complex. You could have 2 conjugate pairs and we never cross the x-axis. Okay, after lunch we'll do 1 to 2 more examples and then talk about your quiz. Okay, so now that we are back together, let's see what we can do with complex zeros. Okay, I have a 4th degree polynomial up here. Yeah, no. Okay. I have a 4th degree polynomial right here. I have given you that we have the 0, 1 plus 3i, and we need to find the rest. If 1 plus 3i is a 0, Amanda, do we know another 0? Okay, we automatically know that 1 minus 3i has to be a 0. I'd like you to do, with your pod, discuss how might we be able to find the other 2 zeros. We have a 4th degree polynomial. We know 2 of them. How will we be able to figure out the other 2? Brainstorm. All right, let's talk about some ideas. Ideas you're willing to share before I start picking on you. Ideas you're willing to share. Jay.
We said we'd multiply the conjugates together and then take that result and divide it, like take the big function and divide it by that.
Okay, so are you saying multiply these zeros or multiply their factors? Okay, so we can multiply the factors together, which would give us what kind of a answer?
Well,
It'd be a quadratic, and then we could take that quadratic, you said, and divide it out of here. Okay? Any other ideas that came up? Connor, do you have something?
No, I really don't.
You can share it for her.
No. No, it's fine with me. I'm embarrassed about. I actually just plug it around in the room with synthetic division.
Well, we could. The only thing is that's going to take some time.
Yeah, and then I went with P over Q, but 60 has a lot of factors.
60 does have a lot of factors. 60 does have a lot of factors. Okay, so let's use the 1 plus 3i. That way we can like narrow it down better. Pod 7. I kind of overheard your discussion. What were you saying?
I don't think it's right, but just like multiply the complex zeros and just kind of see what happens. You know?
Okay.
Or you like synthetically divide the
Oh.
whatever your answer is and just kind of hope it works.
Okay, I like the synthetic division part that you brought up. Okay, could we do synthetic division with 1 plus 3i? And then do synthetic division with 1 minus 3i? We could. Henry's saying, no, I don't want you. Okay, we have 2 routes we can take. We can do synthetic division twice with a complex, 2 complex zeros and whittle it down to a quadratic. Or we can take the zeros, make them factors, multiply to get a quadratic, and divide that out. What do you guys want to do? Okay. So, we know factors of 1 minus, not 1, x minus 1 plus 3i, and x minus 1 minus 3i. We know that those are both of our factors. Those divide evenly into our function. Now we know that if we multiply these two factors, what's going to happen? What should happen with the imaginary numbers? They should go away. Alright, so we have to distribute x times x times negative 1, and x times 3i. Okay, we'll move to this negative 1 times x, negative 1 times negative 1, and negative 1 times 3i. Then this negative 3i needs to be multiplied through, so negative 3i times x, negative 3i times negative 1, negative 3i times positive 3i. Negative 9i squared, but since I squared is negative 1, we can write that as plus 9. Alright. So now what happens? 3ix minus 3ix cancels. Negative 3i plus 3i cancels. And we are left with x squared minus 2x plus 10. That look right? Got it? Okay. Now, if we created these factors with the zeros, since these are factors, we know they divide evenly, correct? So what should be true about x squared minus 2x plus 10? That should divide evenly, because we took two factors, multiplied them to get to here, so this should also divide evenly. So now, what we can do, what's our original equation? We can take x to the 4th minus 3x cubed plus 6x squared plus 2x minus 60, and we can divide it by x squared minus 2x plus 10. I will say on the quiz, long division went pretty well. There was only maybe a couple people who made some small mistakes. But let's talk through this problem together. X squared goes to the x to the 4th how many times? X squared. We multiply our divisor by x squared to get x to the 4th minus 2x cubed plus 10x squared. Okay. From here, we're subtracting, so at this point, we make these opposite signs so we can get the subtraction. Okay. So we are left with what? I need your help. Negative x cubed, right? Plus 2x. Okay. X squared times what is negative x cubed? Negative x. It's working out nice. So x times negative x, negative 2x times negative x, and 10 times negative x. Remember, we are subtracting, so at this point we can make signs opposite. And we are left with negative 6x squared plus 12x minus 60. We brought down the constant. This is the last time we have to go through this. X squared times what is negative 6x squared? Okay, so we get negative 6x squared plus 12x minus 60. And just like that, we have a remainder of 0, which we should have because we use factors to create that quadratic to divide it into here. Okay, so now this was our result. Okay, basically, we figured out that our function is x squared minus 2x plus 10 times x squared minus x minus 6. We already know the zeros from this quadratic. Now we need the zeros from this quadratic. How are we going to get those? This is like the best trinomial of factor, right? What multiplies to negative 6 adds to negative 1. So we have zeros of, what were they? 1 plus or minus 3i. I do not mind if you write them like that. You are more than welcome to write them separately too. Well, we also have zeros of 3 and negative 2. Okay? We could have used the rational zeros test, but it may have taken us a while to get through those, right? Any questions? Great. You have a really short assignment this weekend. Look at that. 1, 2, 3, 4, 5, 6, 7 problems. I just think that's pretty awesome. This assignment should be on your gold sheet.